Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students, so we continue our discussion with a related set of topics to what we discussed previously. So we discussed Newton's laws, we discussed force, right? So now we are going to discuss a related idea, you know. Let me go to which is, you know, allied to the ideas that we have dealt with so far. Okay, when physics is taught, it is taught in an axiomatic way. What I mean by that is, it is taught like when geometry is taught. Okay, so you first have Newton's laws, and you learn to solve problems involving force. Okay, then you learn Newton's second law and its implications in the context of other ideas. Okay, and one of these ideas is what happens when there are multiple bodies which in toto have no external force. Okay, the rate of change of momentum is directly proportional to the impressed force and takes place in the same direction, right? Now, when Newton quotes these laws, always in the passive voice, why you should also understand, right? Because the actors are not specified, you know, the actors, the observers, the actions, all these form part of an interesting mix of players. Okay, so when we look at collisions, right, we actually start with Newton's first law. The rate of change of momentum is directly proportional to the impressed force, right? So now what happens when there is no external force on a system of bodies, right? It still behaves like the forces are only internal, that is between the bodies. And between the bodies, you know that every action has an equal opposite reaction. So if A applies force on B, B applies force on A. But so if you look at the system as a whole, there is no external force, right? Even if they collide, right, then at the point of collision, there is a force between them, right? But the system itself, when there is no external force, because of Newton's third law, there you cannot, nothing changes in the application of the second law. You see? So that's the key idea. So external force. So when you look as an observer at a subsystem, and you're always doing that, it gives you that added opportunity, understanding. Okay? So then, if there is an F equals ma, right, there is an external force, right? Then what happens? Then what happens is you have this force acting over a period of time, and if you integrate dp by dt, right, you write dp by dt equals f, right, or sigma f, and then use or net f, right? So dp by dt equals net f, right, and therefore you say dp equals f net dt. So you integrate f net dt over a period of time, you have p2 minus p1, dp between the limits p2 minus p1, where p1 is happens at a certain time, 2 is at a certain time, right? And then you have f dt between t1 and t2, which correspond with p1 and p2. So you have p2 minus p1. The change of the momentum is called impulse. Okay, so there is that idea. Okay, so when two bodies collide, one transfers some of its momentum to the other, right? So this is the idea of collisions. Okay. Now, when you have a rocket, right? A rocket, what it does is it expels a portion of its own mass outside. and therefore its weight is continuously shrinking as it goes up. Okay, so and a portion of the mass is being ejected, right? So the remaining portion over a period of time is shrinking in mass, and its velocity is increasing at the same time as it leaves the gravity. The gravity is also decreasing. You see, so the force is decreasing because it has gone so far up, right? So it takes less and less and less impulse to move smaller and smaller parts further and further up. Okay, so that's the key idea in rocket propulsion. Okay, and there are other lot of very sophisticated ideas in rocket propulsion. That's why it's a big industry today. Okay, and so you can have lot of it takes a lot of energy to send something to space. $500,000 will get you a trip and back. Okay, so you can buy 10 Teslas, or you can go to space once. It's your choice. Okay, so now, so then you have this impulse caused by an impulsive force, right? And then you have these ideas, right? So now there is this thing called center of mass. Okay, this, when you have multiple bodies, like let's say you had a missile, right? Missile is shot, right? Stinger missile is shot. Some of these missiles, they go up and then they explode. Okay, when they explode, the various parts are pushed in multiple ways. Okay, now, but then the forces that act are only between the parts. Okay, now it's kind of tricky because sometimes when it explodes, there is also an, like, an internal implosion that happens, right? There is a spark, and one part is pushing the other parts, right? The one part is creating energy and also momentum that then drives, still there's conservation of momentum, right? The only force that acts when you shoot a missile is gravity on the system as a whole. Okay? So what then happens is the and when there are five different bodies moving, they talk about the center of mass. Okay. Now, if there is no external force, then there is the momentum stays constant. dp by dt equals 0, f equals dp by dt, dp by dt equals 0 means p is a constant. And when p is a constant, before and after, we say there is what is called conservation of linear momentum. So with that, I'm going to go into the definitions and ideas a little more. So first, there's this idea of the rigid body. The rigid body is such that its shape does not change, or if it does change, it changes for a very negligible period of time. So it will then deform and then come back to its original shape. So now what happens in a non-rigid body is that you hammer it, right? It deforms. So you go hit it, it does not move, it deforms. Okay, so that is very different from this rigid body. When we talk about all this momentum and all that, we're talking essentially about rigid bodies. We state that also. So when we say talk about deformation, there is no deformation. Now there are three types of motion, right? Translation motion, where something is moving in one direction, right? Then there is rotational motion, where something is spinning, right? Sometimes you apply two forces, it will cause something to spin, right? What is called a, like, in you have dipole moment, a moment, right? It causes two equal and opposite forces will cause a torque. Okay, and so then that will lead to rotation. Now, what causes rotation? Torque causes rotation. Torque is the equivalent of force in translation. Okay, so we will deal with rotation the next time, but for now we are we include the third case where there is both translation and rotation. That happens when a ball rolls down an inclined plane. Okay, when what is his name? Ravichandran Ashwin, right? Comes and delivers the ball, right? He is what is called a finger spinner. He uses his fingers to spin the ball. So then he produces both translation and rotational motion. So ball rolling down inclined is not the only case. When Ravichandran Ashwin, Yuvendra Chahal, I don't say the name well, right? Yuvendra Chahal, right? So when he comes and bowls, he's a wrist spinner. Ravichandran Ashwin is a finger spinner. Regardless of whether you use the fingers or the wrist, your aim is to cause the ball to spin, right? And the spin imparted, right, is sometimes the ball will not change trajectory when you bowl spin, right? Sometimes the ball will pitch and it will bounce like that. It's called overspin. Like a lot of time when Harbhajan Singh used to bowl, they would say he's added a lot of overspin, right? When Yuzvendra Chahal bowls, he adds what is called a top spinner, right? Then in the old days, there was also flipper. Okay, all these are translation and rotation balls deliveries. Okay, so you, I was not trying to teach you spin bowling. Okay, my aim here is to teach you Newton's laws. We already discussed Newton's first law, already discussed Newton's second law. Now we are going to discuss center of mass. When there are n bodies, then the the center of mass is the weighted average of the positions of the n bodies, as though it is restricted to a particular place. Okay, so it is, if there are n bodies, m1, m2, m3, m4, m5, mn, whose net weight is m1 plus m2 plus m3 plus mn, equal to capital N, the n bodies at there are n bodies at n places, at n different places, right? The n bodies at n different places, each is in a different place, and the location of each of the bodies is defined by the vector Ri. The position of the ith body is Ri. So sigma mi Ri from I equals 1 to n is the divided by m is called the center of mass. It is a vector. The location of the center of mass is a vector. Position is capital R Cm. Okay. Now this is nothing but a vector weighted average. Sigma mi Ri by m is the vector weighted average. So it is, if you replace all these bodies with one body at RCM, it is the same thing. Okay, you replace n bodies whose weight is m1 plus m2 plus m3 to m, capital N. Take that and replace it with one body whose center of mass is at RCM. So mr equals m1r1, m2r2, mnrn dot 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 mnrn, right? So mr equals m1r1 dot dot sigma mi equals mr. Okay, so now you differentiate both sides. You write m dr by dt, where r is the position of center of mass, m times drcm by dt equals m1 dr1 by dt, m2 dr2 by dt, dot 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 dot, right? So then you can say m vcm equals m1 v1 plus m2 v2 dot dot m1 mn vm. Now you take the derivative a second time, you end up with ma equals m1 a1 plus m2 a2. That is, so you have ma equals m1 sigma mi ai. Right? In the previous case, you have MVCM equals sigma mi vi. Right? M times VCM equals capital M times VCM equals sigma small mi vi. Okay? So the sum of the momentum is the total mass times the times the velocity of the center of mass. Okay? So M times V gives you the total momentum as well of the entire system of particles. Remember, when we talk of some of these vectors, it does not have a The sigma is independent of location. When you do a sigma from different, right? So so remembering that there is a certain independence there, sigma m times v equals m1 v1 plus m2 v2 dot 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 m1 mn vn. So these are the three equations, right? So now if there is no external force, P is equal to constant, and this we call as the conservation of linear momentum. Linear momentum of system of particles with no external force remains the same as you know, right? So when there is no external force, there is some interaction between the particles. The momentum is conserved. The momentum before, the momentum after does not change. It just gets transferred between the bodies, with respect to each other. So this is a very key concept in collisions. In collisions, regardless of the type of collision, whether it's an inelastic collision, semi-inelastic collision, or completely elastic collision, momentum is always conserved. Momentum is always conserved if there is no external force. When is the momentum conserved? There is no external force. Momentum is conserved. That is the most important rule in collision. And momentum is a vector rule, right? Now, there is, based on the level of elasticity in a collision, a completely inelastic collision, there is only momentum conservation. Completely inelastic collision happens like this. I have one ball, another ball comes and hits it, they both go together like that. That is a inelastic collision. Okay. Now, if they hit and then they go like this, there are two possibilities. They hit and move away from each other. There are two possibilities. Momentum is always conserved regardless of the possibility. Okay. One possibility is when there is, if they hit each other and then they collide and move like this, it's an inelastic question. But if they hit each other and move like this or like this, right, then it is semi-elastic or perfectly elastic. When it's perfectly elastic, kinetic energy is also conserved. When it's perfectly elastic, kinetic energy is also conserved. Let me say it one more time. Only when it's perfectly elastic, kinetic energy is also conserved. So you will have both a momentum conservation and a kinetic energy conservation only in a perfectly elastic collision. In between the inelastic and the perfectly elastic, there are a range of semi-elastic, semi-inelastic collisions where only momentum is conserved, and we introduce this term called the coefficient of restitution, E. Okay, so coefficient of restitution is the ratio of the change in the final velocity divided by the change in the initial velocity, or the difference in the final velocity divided by the difference in the initial velocity. V1 minus V2 is the V1 and V2 are the final velocities. U1 and U2 are the initial velocities. V1 minus V2 divided by U1 minus U2 will give you E, which is called the coefficient of restitution, coefficient of resilience, coefficient of restitution. Okay. For a perfectly elastic collision, E equals 1. For a perfectly inelastic solution, E equals 0. What does E equals 0 mean? E equals 0 means the numerator is 0. What does the numerator being 0 mean? V1 equals V2. Only under those circumstances, E is equal to 0. So perfectly inelastic implies E equals 0. So in between, there are all these quasi-inelastic solutions where E is not 0, nor is it 1, but it lies some number in between. Therefore, and E is the ratio modulus of V1 minus V2 by U1 minus U2. So now, you can also have oblique collisions, right? When you have an oblique collision, these two bodies hit and one goes like this and the other goes like this. I'm sure you've all played this game called carom, right? Or you have used this pool, billiards, right? Billiards or carom often involve oblique collisions. That is, one hits in an angle, the other moves in one angle, this one moves in another angle. Now, there is a stationary body which experiences an oblique collision, right? So if you have an elastic collision, Post collision, the angle between the two bodies is always 90 degrees. Remember, this is only for oblique elastic collision. If it is not elastic, you cannot use this angle between the bodies is always 90 degrees. Obliquely against, when there is a moving body, it's a stationary body, 90 degrees. Oblique elastic collision only if it is elastic. Remember these things. Oblique elastic, see, normally when they deal with elastic collision, they talk of head-on collision, right? In when I would watch Hindi movies, Tamil movies, etc., they would talk about this head-on collisions, direct, right? And they would say on the spot, head-on collision on the spot, right? So avoid head-on collisions. Okay. Now, elastic collision in one dimension we already discussed. So, but let's understand how to make it work. So, what is the first law? There is always conservation of momentum, right? M1 U1 plus M2 U2 plus M1 V1 plus M2 V2. Now, if there is an elastic collision, then also kinetic energy is conserved. When is 2 true? When there is. When is 2 true? When there is. When is 2 true? When there is a perfectly elastic collision, right? That is when energy conservation happens. 1 is always true unless if as long as there is no external force. Okay. So now when 2 is true, this is the other rule that E is 1, which means V1 minus V2 by U1 minus U2 equals 1, or actually it is negative 1. Okay, because they have that modulus. If you remember the modulus, right? And so the modulus is replaced with a minus sign. Minus V1 minus V2 equals U1 minus V2. So then you solve these two. Typically, you take this equation and you use that in this equation, right? Remember that V1 and V2 we are solving. U1 and U2 are known, typically. Okay, unless they change the question a little bit. In case you can still solve. Okay. Now, so this is the first case. Now, if it is a perfectly inelastic collision, remember V1 equals V2. Okay. So now, using these two, if M1 equals M2 and U2 equals 0, so one body is at rest, another body comes and hits it, then what they are saying is this body will stop and this body will move with the velocity of the first one if it is a perfectly elastic collision. If one body is this big, right? If M1 is very big with respect to M2, right? And U2 is 0, a big body comes and hits it, it's just going to get steamrolled. V1 will be equal to U1. But the second body will have a velocity which is twice the U1. Okay, so remember these two rules. Okay, this is all collisions. Okay, two bodies A and B initially at rest move towards each other under a mutual force of attraction. Okay, so what does that mean? Mutual force of attraction, right? What they are saying is at the instant when the speed of A is v and the speed of B is 2v, the speed of the center of mass of the system is what? This is a trick question. Two bodies are initially at rest. Then they start moving towards each other under the mutual force of attraction. There is no external force. If there is no external force and they are initially, there is conservation of momentum. If their initial momentum is 0 because they are initially both at rest, their final momentum will also be 0. Therefore, the answer is D. There is no external force. The center of mass is initially at rest. Therefore, there is nothing will happen to the center of mass. So, remember how he is confusing you by using this word speed. Speed is being used to confuse you. So this one, incidentally speaking, A is V and 2B is a little bit like this. It's a little bit. It's actually not like that. Because both of them are initially at rest, right? So the point here is there is no external force. So there's no external force, only internal forces. There is no, there's conservation of momentum, and the initial momentum is zero, so the final momentum is also zero. Okay, remember, we are doing problem solving, right? So this is essentially to teach you the material if you missed it first time. So if you are a class 11 student, you've done almost one semester, 6, 7 months, right? So now this is the time class 11 students are fully deciding, am I going to be NEET or am I going to be JE? Am I going to be state board? Am I going to be CBSE board exam? I'm going to study hard and do well. Two blocks of masses 10 and 4 are connected by a spring, negligible mass, and placed on a frictionless surface. An impulse gives a velocity of 14 to the heavier block in the direction of the lighter block. The velocity of the center of mass is what? Right? So what is the initial momentum? 10 times 14, right? So now what happens to the center of mass? It is, the new mass is what? 14, right? So 140 is the initial impulse, the initial momentum pushed to the first one. The velocity of the center of mass will become 140 divided by 14, which is 10. M1v1 plus M2v2 equals MCVC. We already looked at that. This one, okay? This equation, okay? So learn the ideas and then physics becomes very easy. Now, the second rule is if M1 is far, far less than M2 and U2 equals 0, then V1 equals minus U1, okay? So heavy ball, little ball goes and hits a heavy ball, right? Then this little ball going to go backwards with the same velocity, and the big ball is going to go slowly this way, that way, given this rule. Okay? So these are all when you solve for this, and then he's plugging in the answer here. Now, my advice to you is you take this equation and this equation and produce this equation so that you can very quickly learn, and otherwise you solve it once and then you also remember it, memorize it, right? So how do you solve this? You write V1 equal to U1 minus U2 plus minus V2, or V1 equal to U1 minus U2, U2 minus U1 plus V2. U2 minus U1 plus V2 equals V1. So you take that and plug it into this one. Then you will be able to write V1. This right side will become entirely based on U1, U2, and V1. Keep the V1 terms together. Therefore, you'll end up with M1 plus M2 times V1 equals something, right? In the second case also, when you replace V2 with this, you will be able to reduce it to V2 equals something. Okay, so that is your goal here. Your goal here is to learn to solve this using these equations. Okay, so and then look to take the case when M1 is very big and M2 is very big, when U2 is 0, U1 is 0. Okay, so solve, and then these are all results that directly come from solving that equation. You can M1 equals M2 equals M, then U2, then V1 equals U2, right? Particles exchange their velocities. The second body is at rest. The fractional decrease in the kinetic energy of mass is given by, right? If second body is at rest, the decrease in the kinetic energy of mass M1 is given by this equation. That again you can derive. This is in the case of elastic collision, still in elastic collision. Already looked at this. Okay. Now, the total kinetic energy of a two system particle relative to the center of mass, total kinetic energy, right, can also be derived. So this one we've already derived, right? So now the total Ke is equals half times m times VCM square, right? So the Ke of M1 is half times M1 times VCM square, The KE of V2 is this. The total KE is the sum of the KE. Okay. Otherwise, you can calculate the M's and the and then do half times M1 plus M2 times V2 square. So now the KE with respect to the center mass given by that. Now, potential energy is the energy possessed by a body as a virtue of its position. Right? We call that potential energy. So now that is not necessary. So now let's look at this question we already looked at. So now inelastic collision, right? In inelastic collision, E equals minus V1 minus V2 by U1 minus U2, right? That is the coefficient of restitution. Now, then when you use this, here again you can replace the V, you can write V1 in terms of V2, U1 minus U2 times E times something else, and then plug it back into this, and you will end up with these two equations. Okay, if you memorize this one, you have a good memory and you can memorize this one, you can just put E equals minus 1 and you will end up with the perfect elastic collision. And then you can use that to solve these other equations also. Now, in perfectly inelastic collision, there's only one variable. Luckily, there's no V1 and V2. V1 equals V2 equals V. And therefore, you can very easily solve it, right? So you just have one equation, which is M1U1 plus M2U2 by M1 plus M2. Right? So that is perfectly inelastic collision, right? So that is just from the conservation of momentum, you can solve, right? Now in oblique collisions, you have two equations and two, because you have two dimensions where you solve for momentum. Remember, momentum is a vector, therefore it has to be conserved in both dimensions, x and y. There will be conservation of momentum. See right here. A ball of mass m moves with a velocity along x-axis, strikes another ball of mass 2 kept at rest. The first ball comes to rest after collision, and the other breaks into two parts. See this. Two parts. First ball comes to rest after collision. The other breaks into two parts. One of the pieces goes along the y-axis, this piece, the speed v1. What is the velocity of the other one, right? So there are two equal pieces, right? Now, why did I pick this direction, right? See, the initial momentum is what? M times V, right? Now, this one, the first ball comes to rest, m times v goes to 0, right? The second ball has two velocities, one along y and the other has to be like this. So that one part cancels this and the other part, the horizontal direction component of the velocity equals 2 times v. So it has a 2 times v in this direction and a v1 in that direction, right? So what is the angle? What is the velocity of the other piece? It is v1 square plus v square, right? Because this direction is what? Started with 2m times v, right? So the initial momentum was 2m times v, right? So the final momentum also has to be 2m times v. So it has to be 2v in this direction. This is wrong, right? It has to be 2v in this direction, right? Okay, so it has to be 2v in that direction and it has to be v1 in this direction. So it has to be 4v square. Let's change it before anybody finds out, right? 4v square, right? Initial momentum was 2m times v. Net final momentum after mv is 2mv. And one piece is going v1 in that direction, so the other piece is going v1 in this direction. It'll have v component v1 in this direction. is V1 by 2V. Okay, so that is the tan theta, V1 by 2V. Okay, so don't make mistakes like I make. Okay, so keep that in mind and let's go to the next problem. Okay, consider the situation in which a baseball is delivered towards a stationary wooden board by a pitching machine. The machine is set to deliver the ball at the 0.145 ball at 10 meters per second. Ball hits the board, makes a 45-degree angle. Board is slightly flexible and the collision is inelastic. Ball bounces at an angle of 40 degrees from the surface. What is the velocity of the ball after the collision? Right? So this is right. What is the if the ball is in contact for what is the magnitude of the force of the ball on the ball? Right? How much work was done on the ball by the ball? Right. So now the what gets conserved? Right. Well, it hits the board, right, and then it bounces off. So the fact that it is inelastic, right, means that what is the initial momentum? 10 times 0.145 at 45 degrees, right? So now that has a component in this direction, right? In the horizontal direction, that has a component of 10 times cos 45. So 10 times cos 45 in the horizontal direction will continue to be there, right? Now, after it hits, there is a component. So now 10 cos 45 in this direction and some unknown value, right? And then 10 sine 40 in this direction is going to give you the net so the what is the velocity after the collision, right? So now see what is conserved, right? That is the first question, right? What is conserved in the horizontal direction, that is in this direction, momentum is conserved. Now in this direction, right? So one thing you do know is that 10 cos 45 is the horizontal force. What you don't know is V. Okay, V cos 40 will equal 10 cos 45. So what is V? Right? V cos 40 equals 10 cos 45. That's the only thing you can use. It's inelastic. It's not perfectly inelastic. Nobody knows the whole story there. Okay. So what you do know is V cos 40 equals 10 cos 45. Okay. V cos 40 equals 10 cos 45. Therefore, 10 cos 45 by cos 40 will give you V. Now, if the ball is in contact with the wall for 0.5 milliseconds, right? So now, once you calculated V, right, then you can calculate the vertical component. Okay. Now, once you calculate so V sine 40 will give you the vertical component. So V sine 40, right? So 10 sine 45 minus V sine 40 is the change in the momentum of the ball, right? That the change in the momentum is the impulse. That is the impulse applied by the board on the ball, right? And that is the impulse also applied by the ball on the board. That is therefore, that change, delta impulse divided by 0.5. Impulse by time will give you net force, average force. Okay? So impulse by time will give you the average force. Now, how much work was done on the wall by the ball, right? So SDS is actually the work done, right? Now, but you cannot calculate that. What you can calculate though is the change in the kinetic energy. The change in the kinetic energy of the ball is initially it is half times 0.145 times 10 square. The final thing is half times 0.145 times v square. We already calculated v from this here, right? The change in the energy is the work done. Okay, so that is how you solve for all three. Okay, so so what is to be learned from this? What is to be learned from this is that when you solve collision problems, you must know whether it's elastic or inelastic, whether momentum is conserved or kinetic energy is conserved or what is conserved. You must know how to use these things in solving these problems. This is very, very critical. Okay. Now, see, this one, a projectile is fired at a 50 meter per second at 30 degrees above the horizontal. At the highest point, what happens at the highest point? There's no vertical velocity. In the horizontal direction, there is no force. 50 times cos 30 is the horizontal velocity. So that is what is the in the vertical direction is energy conserved? No, energy is not conserved. But in the horizontal direction, momentum is conserved. Only in the horizontal direction. In the vertical direction, momentum is not conserved because there is a force. What force? Gravity is there. Okay, so it breaks into two pieces. Ratio 1 is to 2. Okay, now the larger part comes to rest. The smaller part is 1/3 of the mass. So initial momentum is what? 50 cos 30. Final momentum is what? 1 by 3 times v, right? And so that will give you the 1 by 3 times v, right? Therefore, 50 cos 40, m times 50 cos 40 equals 1 by 3 m times v. So m cancels. You end up with 3 times 50 cos 40, right? So in the horizontal direction alone, momentum is conserved. Find the point where the smaller ball lands, right? Bigger one comes to rest, the smaller one is going to go going at a faster rate, right? So from that point on, you solve another projectile problem for the smaller ball. So these are the types of questions you will always get in physics, in mechanics. These are very classical mechanic problems. They will twist and turn, but they're all actually just application of Newton's laws, application of vectors, application of conservation of momentum. You must know what is conserved, what all are conserved, how to deal with these things in the context of Pf minus Pi equals integral f dt. I already explained that impulse and impulsive force. When you apply a force over a particular direction, there is a change in the momentum. And what is the change in the momentum? Pf minus Pi equals integral f dt. dP by dt equals f. Therefore, integral f dt Ti to Tf will equal Ps minus Pi. Okay. So with that, I'm going to stop for today. I know you have all learned a few things here, and you should use our app com.nyalmarga.sushruta if you're a NEET student, com.nyalmarga.ramanujan if you're a JE student. Use our app and then go to the Google Play Store, use our app, and then learn from that and then solve problems. Use the assessment. We now have very good assessment as part of the app. So with that, I'm going to stop for today, and I'm going to ask students to learn this material and then solve problems. We are in the second part of the cycle of the material for class 11. This is the time when you really must consolidate your everything that you've learned on in mechanics. If you're taking NEET or JE, this is extremely important. Once you master these three things: calculus, mechanics, and calculus, vectors, and mechanics, you have laid the foundation that you need for physics. And do a lot of problems at this time so that you really build mastery over this material. This is very critical material. If you get this 50% together, you're well set to do very well next year. Take it from me. Take it from me. This is the time, students, you have the most time to build a lot of mastery over these three things: calculus, um, mechanics, and allied subjects. So if you are a smart kid, you will do waves now. You'll do simple harmonic motion and waves, and also heat. Get all this together, you'll be in very good shape going into your class 12. So with that, I'm going to stop, but do a lot of problems now, because this is the problem side of the learning. If you miss the material the first time around, I re-explain it a little bit, but then this is the time when you're doing both. Then you have to do both now. You have to learn the material again carefully, look at the IIT PAL lectures, read the textbook, look at H.C. Verma, concepts of physics, and do well, do well. I'm counting on you. Parents are counting on you. I'm counting on you. I want to say, he's my student. She is my student. All right. I'll see you next week. This is for the class 12. The class 12 students, be seeing you tomorrow. I'll be seeing you tomorrow. Please come. Please come. All right.